Professor, we can't hear you.
Ah, sorry. Okay. Funny. Can you hear me now?
Yeah.
Okay. Oh, weird. All right. That's so weird. I'm so sorry. I'll repeat everything. I was actually saying something. It's really weird that that just happened because, it's probably the first time I didn't directly ask you if you, so it really goes to show how important that conversation is when I ask you if you can hear me. Okay. So sorry. Right. You totally couldn't hear me. Okay. Um, but you can now. Okay. And I can hear you now. And I love it. Um, and all right. This will give me a chance to do draft. Of course, the first version of whatever I say is always too long anyway. I was basically just trying to say, I think you guys are doing great. I think, again, I owe you more at this point than you owe me. Like, I mean, some of you may feel very behind and some of you might be very behind. Like, I do know from some personal conversations and some of you still might not know what's going on at all, partly just because the whole Zoom thing is so hard or because life is life. But I feel like more and more of us have more of a chance to know what this material is and are really getting it. And I feel like the material is moving forward through you guys in a way that is starting to be, even though it's like painful and inefficient, I'm starting to get where the material is for a lot of you guys in a way that can actually be more precise and personal than sometimes even happens in real classes. Just so you know, I'm just saying, I think you guys are now being so patient with me and working with me. I think many of you really are positioning yourself, not only definitely for a very good grade that you should not be overly stressed about, like you should start, especially you'll see with the midterm, you should start, maybe you already do from 203, start believing that if you just keep doing what you're doing, the grade is not going to be a crisis. And also, I think a lot of you are really learning something and really figuring something out here and are going to be good positioned for like, deeper stuff later, like research and stuff when the world comes back together, if it does. That's all a compliment that I want to give, just to be like, so I think the system is working and we will talk about an exam soon and it shouldn't cause undue stress. But all that, and I will put another portal in the Google thing and I owe you more points and all that. Today will be a little different though. Just all that said, I think it's working really well and I don't want to change the system. Today's going to be a little faster in two respects. One, I'm going to talk once I'm going to do a little bit of material that's just me talking. I'm going to just run through something that some of you might have already figured out or understood from lab, and some of you might not, whatever. Do that. Oh, excuse me, hold on. And I'm not going to turn it into a question, really. I'm just going to show you something. So it's going to be a little faster in that sense. And please, and it is important material. Again, some of you will be bored by it right away because you already get, some of you, it will be too fast the first time. And I have to tell you in advance, it's the kind of material you'll have to look over a couple of times before it actually, like it's not meant to be fully understood the first time. It's meant to be like written down the first time. So I'm going to do a little material like that in a minute, like lecture-y. But hopefully it's not that long and fast. And then I'm also going to cut class early, I think today. I think we're going to go early because I have to. So it's like but still anybody who even said yes or that I can't hear like 5 minutes ago, that counts for 50 points today. Okay, I'll put the portal in and all that. But so I apologize in advance. This material will be, it's material we're going to do. I'm going to fire through it a little bit. And then I'm going to hope to cut us all loose. How early? I can't, I know anything I say, I'll fail. So I don't want to say, but I will tell you this. If I got through this material in 15 minutes and I felt like at least it was complete package that you could read, then I wouldn't have any problem leaving right then if you didn't. That's sort of my goal. I'm sure I'll fail. Okay, so I'm gonna do, just gonna put a couple equations together for everybody right now. Again, ideally, maybe some of you already get this from lab, or you're in the process of getting it. Or this will help you write your post labs or your reports for lab 3 in particular. But who knows? Whatever it is. So is it? Can I just get a show of hands or electronic or whatever? Is it sort of clear what I'm saying? That I'm gonna just lecture a little bit here, but kind of fast. But then we'll go early. Is that cool? And is that okay? But okay,
Yep,
cool.
sounds good.
Thank you. Great. All right. You're so human. One day we're all gonna have a post-virus, post-physics party. I'm gonna meet all you people, and I'm gonna be stunned to find out that you actually are as cool as I think you are, and you're gonna find out that I'm as much a mess as you think I am. Okay. All right. So actually, so here's the deal. Okay, so remember our picture of a whole like row of identical vertical oscillators that are all the exact same kind of oscillator, all same K, all same M, let's say, or all same omega, more importantly, but all staggered in phase by a constant amount, right? A collection of staggered oscillators, which then what we're trying to say is that's one and the same thing as a wave pulse. Like that's what so far we're saying in English, a collection of staggered oscillators. In other words, a system that oscillates in time and in space, a system that can be described by cosines in time and cosines in space. That group of oscillators is what ultimately gives rise to a wave pulse, something that moves from here to there without there being anything moving from here to there. Like that's what we're saying so far in English, right, in the class. And what we're saying mathematically about that, or where we could, our collection of harmonic oscillators, we said, look like this. And, and each time maybe we write it slightly differently, but basically we've been writing it like this. Right, where that K is angular wave number, radians per meter, that omega is angular frequency, radians per second. And that K, I draw fancy just to make clear that it's not the K of Hooke's law. It's like a different K. It's not newtons per meter, it's radians per meter. Okay, so this was a collection of staggered oscillators, we said. It's this business. Right, and I hope so. But what goes? Oh, right, so for example, if there's a bunch of masses on springs, we observe something move horizontally through this horizontal row of vertical oscillators. The only things moving are oscillators, are masses on springs, but every single mass on spring only moves vertically. Like we get this pulse that moves horizontally, but there's no individual object that moves horizontally at all. Like that's the coolness of it, or that's like the waviness of waves, right? So here's what I want to do for everybody to make sure it's clear. What we started saying last time is this description is a function of two variables. Right. Oh, and oh yes, I even did do this last time. Right. So we said this is a function of two variables. So when we take derivatives of it, we have to take them partially. We take one derivative with respect to time, and in so doing hold space constant, and then we take derivatives with respect to space, holding time constant. Just like in lab 3, you can focus on one bit of space in your like the movie that you make of like a ripple going down a string. You make a movie, right? And then you can either focus on one frame, which means holding one time unit constant and looking how y varies as a function of x, or you can look at one x value and look at how y varies as a function of time. Either way, you get a cosine function. This is the essence of waves, right? So we can take derivatives either way. This is, I know we did this last time. Okay, so just to review, or just to do it quickly again, we said if we take the partial derivative of y with respect to time, so we pretend that everything else, like even though x is actually a variable here, like there's two independent variables, and that's very new for us. Like it's new and exciting, or new and intimidating, but new in physics and new in math, we have a function of two variables. We're going to take derivatives with respect to each variable separately, which means pretending the other one is constant, holding the other one constant like you would in an experiment. So, and I know I said this last time, I'm sorry to say it, but just to, so we got, when we take one derivative, we got negative omega y, this, right, from chain rule. Only the omega comes out because I'm only treating t as a variable. This is what we said last time. Then if I take another derivative, just like we always do in physics, then the omega comes out again, but now we flip back to cosine, but we still have the negative sign. Like this always has happened to us before. Like we've seen this before, I'm just doing it again. But now that's the second partial, that is the second partial derivative of y with respect to t. Like that's what that is. Now on the next page, I'm doing something again that I did do last time. And I think everybody should rewrite it again with me, because like this, it's easier than memorizing it. Just get to know it. But I'm now going to take two derivatives with respect to space, again, of the same function. The function is this, and I apologize. Oh, sorry. Yeah. Sorry.
Can you go back really quick?
Absolutely. Sorry. Absolutely. And one thing going back, I realized, so I'm saying this equation, like I'm saying this is the equation that we're all like looking at that we, but, and I'm writing it as y equals y naught cosine, blah, blah, to all of you. I mean, to all of you, sometimes that y naught I write as a. I'm completely loose between the two of them. I treat them interchange. So, and I don't mean to be confusing, but a and y naught, as long as we're talking about a y equation, they mean the same thing to me. So I apologize if I go back and forth, but you can always write either a or the variable naught. Either one is totally fine. I don't mean to be inconsistent, but okay. So should I go to the next page, or is that good? Or
Yeah.
okay, cool. All right. So now on the next page, we're still dealing with the same equation. I'm trying to tell everybody, like, we still have this same equation, and what this equation again describes is a whole bunch of oscillators, right? Like lined up on the x-axis, but each one free to oscillate on the y-axis. Like that equation captures a whole bunch of oscillators at the same time. And when it answers the question, like if you name a time that you're interested in and you name a position in this row, like you name x equals 7, that in effect means you're naming the 7th oscillator, then I can tell you how high that oscillator will be at that moment. Like that's what this equation is saying. So it's like describing a whole rippling system. And we just took this two derivatives with respect to time. Now I'm going to do the same thing with respect to space. Like what is the derivative of this, the rate of change as we gaze our eyes from left to right along the system, but at one moment in time. This is like when we're just looking at a photograph asking what's happening across the x-axis. Well, we take one derivative and we get like this. That's one derivative. And if we take, so this time you see, I'm saying to everybody, it's the k's that are coming out, not the omegas, because we're doing the derivative onto x. Like we're treating x as the variable now, and we're treating t as though it were a constant. So the chain, we're doing the chain rule either way, but we're getting different results because we're treating two different things as variables. So the k comes out again. Okay, this now right here is as far as we got 2 days ago, I believe. Like I sort of asked you, look at these again. I don't know exactly where your brains are from lab or where, but this is where we ended up last time. I just want to make sure you see where. And I asked you to consider, like we now have something to consider. Specifically, I want to relate these two derivatives, because it looks like, I mean, because frankly, I feel like we now can handle differential equations. This all our understanding of all this came originally from busting apart the differential equation posed by a harmonic oscillator. Well, now we have a whole bunch of harmonic oscillators, and it's making this, to me, cool thing called a wave pulse. It seems reasonable to me that we could be able to capture this in a differential equation like before. That's where I'm trying to go with this. That's why I'm taking derivatives. So specifically, look, I have this, and I have this, like two different second derivatives of the same equation. They look very, very similar, but they're not identical. So it looks like they're related. I mean, they are related. They're not the same, but they're related. So I want to relate them directly. Here's how I'm going to relate them. This is a thing, again, you might have done on your own, or you might have done in the lab, or that. What I do now, so I have these two equations I want to relate. That I want to relate the second time derivative to the second space derivative of this affair, of this collection of staggered oscillators. To me, the simplest way to see this, I'm going to write it on the next page, but what's similar about these two is they each have like the y naught cosine blah, blah, blah thing. That whole piece is in there. They only differ by the constant before it. So I'm going to rearrange each one. I'm going to do it. I'm just telling you in advance so it doesn't confuse people. I'm going to take each one of these equations and solve for the y naught cosine omega. I'm going to isolate the y naught cosine omega t plus kx. The part that's similar, I'm going to get it by itself in both cases. You'll see, but that's what I'm about to do so that I can then set them equal to each other. So if you get what I'm saying, you can do it yourself without looking, but I'll do it. So first I'm just rewriting exactly what we have there. Oh, sorry. And remember, these are partial derivatives. This is a new thing that we've learned. It's part of what we're learning. So it is a different symbol. It's that funny D. It's not a regular D. It's supposed to really be partial derivative is equal to this. Okay. Okay, cool. So everybody see what I'm saying so far? Like I'm trying not to say too much, but I rewrote out. So we found these two derivatives. I wrote them out. I noticed there's like a very similar piece in each. So I take each equation and divide by, like I divide the first equation by omega squared. I divide the second equation by k squared so that that similar piece is by itself on the right side. Therefore, like that's, so from the top I get, oh, negative y naught cosine equals the left side divided by omega squared. And the other equation, this same thing, equals the left side divided by k squared, right? So I'm going to set, so if you follow what I've just done, I just rewrote each equation in terms of its shared identical piece. So these two equations that I just wrote down after the word so, like the negative, they both must equal each other is what I'm trying to say. Because if both things equal y naught cos omega blah blah, then they're equal to each other. So that's what I'm going to write on the next page. Right? I think if you want me, I can go back. Yeah, I can go, but this is what I'm saying so far. If anybody's okay, and therefore, okay, I'm going to go to the next page if it doesn't freak anybody out. I'm going to go to the next page. I'm basically going to write the same thing again, but we're basically at a conclusion now. We're like almost there. And this is like and you might recognize this from lab or you might not, but this is like a finding here we're about to arrive at. I'm just going to write it one more time on the next page, give myself a little more room. But we have so far, we seem to have. Excuse me, sorry. Okay, we're almost there. Well, I mean, we are there. I just have to sort of talk about what it means that we're there. And I've talked about this constantly, but what we have here at the top of the page, what we seem to be saying, like is that once we set up a collection of oscillators and we describe them with that equation, if it's the first time we've ever seen an equation, a function of two independent variables, like a effect that is driven by two simultaneous yet independent causes, right? Like that's what we're saying is going on here. Again, the effect is height, and the two independent causes are time and like horizontal position. If we take a couple of derivatives, we find this differential equation. Like we've now arrived at a differential equation that seems to describe some system in nature or capture some behavior in nature in much the same way that an original differential equation, which led us to all this, did in the first place. Like, so I want to remind you, like, so I'm saying it's a big deal that we've now landed on a differential equation, such a tidy, certainly intimidating looking, but simple, small looking package that seems to contain a ton of information. Like that's what we seem to have here is a differential equation that captures very complicated, but very, very productive behavior all in one simple statement. The simple statement comes in the same form as what we've been playing with for a month, which we're all getting used to. Like it itself is mathematically intimidating. But remember, what we've been playing with for a month is just the mathematical way of saying Hooke's law. Like as long as and remember, we've been saying over and over, it could be true of any dependent variable at all. So it's easiest right now to picture the dependent variable called vertical position. If you just picture a spring, right, a vertical spring oscillating harmonically up and down and up and down, what we've been saying for like a month is that system is described by a differential equation that says, like what does Hooke's law say when it's written this way? It says, we've got a situation where the rate of change of vertical position with respect to time depends on vertical position. Like that's what we've been trying. That's the essence of springiness, is that the rate of change of where you are on the spring depends on where you are. And if you think that sounds kind of weird or funny or a bit like, then you get the point. Like it is weird and funny. The second derivative with respect to time depends on the thing itself. But that's where we get springiness, but that's the nature of oscillation that we've been sort of like playing with for months. But what it says is that the second time derivative of some dependent variable is directly proportional. Let me write this, in fact. This says in English, what we've been saying is that, and I am watching the clock, I promise. The second time derivative of some dependent variable, which in this case is like y, is vertical position, but second time derivative of some dependent variable is directly proportional to, this is the key that we've been saying, the essence of Hooke's law, the thing that actually does make it hard, that actually requires all this calculus and weirdness, and requires us actually talking about it for like more than a month, which I'm sure seems crazy to anybody that's following. But like the reason we spend so much time talking about oscillation is because it has this crazy quality where the rate of change of the thing depends on the thing itself. And when I say depends on, what I'm now saying even more specifically is directly proportional to. Like the whole essence of this differential equation, the cosine solution, everything we've been doing is that it's saying the second time derivative is directly proportional to the variable itself. By directly proportional, what do I mean? I mean it's equal to the variable itself times some constant, and maybe even a negative sign, but that's also a constant. Like directly proportional means equal to times a constant, right? So now let's look at this new differential equation that we just developed. And the point I really want, it's a new equation. It looks like the old, it starts like the old because it's saying on the left-hand side, what's the second time derivative of this variable equal to? And then notice on the right-hand side, it says, oh, it's equal to a constant times something. Like, so again, what we have here is second time derivative is directly proportional to something. The catch here is it's one step more complicated now, because now on the right-hand side, instead of just having the variable itself, which already was weird, now we have a different second derivative of the variable. So this is definitely more complicated. I mean, that's why I'm pausing on it. What this is, oops, sorry. What this is our second differential equation. And it's built from the first one, but it's deeper than the first one, because this one this is on purpose, this new differential equation is identical to the other one on the left-hand side. Both of them relate the acceleration of something, both say the vertical acceleration of something, the rate of change of position with respect to time. They both relate it directly proportionally to something. Hooke's law says it's directly related to the position itself. This equation says it's directly related to the second space derivative of position. Now, what that means, I have to tell you, but let me start by saying this whole thing, which embodies oscillations in time and in space, but which is built from Hooke's law, this thing is called the wave equation. It is, and you may know that from lab 3, or you may recognize it from, it's sometimes, and just like Hooke's law, it can be written different ways. Like the constant can be written a number of different ways, one of which we may get to today, we may not. The constant in there, so in fact, I'm going to go to the next page. I'm sorry. The wave equation, let me write it again. As far as I'm concerned, the wave equation is this. Which means you can also see it written this way. The wave equation says that the second time derivative of some variable is directly proportional to the second space derivative of the same variable. It says, and you can write it either way, because whatever's in that parentheses is just a constant that can be expressed different ways. And it's just some number that I don't know. But if you want to flip the variables and if you want to write it in terms of the other one, like might happen in lab or might happen in another proof we do, if you want to write it the other way, that just means dividing both sides by the constant. And a constant divided by a constant is still a constant. So in other words, you may see it this first way, you may see it the second way. They're both equivalent, but they are both the wave equation, which is a second order differential equation. They are the wave equation. How we use it and how we solve things with it, I'm going to wait till next time. But one place it comes from is everything we've been saying. It's just, I came from taking two derivatives of the position function with respect to time and with respect to space. I want to do a little bit more with this, and then I am going to, wait, it's a quarter. Yeah, I'm going to go a tiny bit more, but I think you're following me so far. And I don't mean to say people can't ask questions, but I certainly don't mean to imply if anybody is following this at all enough to have a question, please do stop me. I just mean I'm not going to stop to construct questions as I would prefer to do. But if you're following this so far, and again, maybe you recognize this from lab, and that would be great if you did, or if you vaguely recognize it, but you didn't understand in lab, going back and looking, it may help now. So the constant can be written different ways, but right now I'm writing it the way we just got. Right now what we have is this. And honestly, what's amazing about this equation Okay, what's astounding about this equation, one of the main reasons it's so important is this equation is remarkably simple in one way. It's just like F equals ma or distance equals rate times time or something in one way, in that it just makes a linear relation between two things. It's just saying the second time derivative of something is directly proportional to the second space derivative. So this is literally is a y equals mx plus b type equation where b is 0. So in that sense, physicists and mathematicians and scientists like nothing more than linear equations. Like nothing can get simpler than this equals that times that. That's what we always want in life. And that's what this is. It takes all the characteristics of wave motion and puts it into this linear equation where it's just, where the slope is omega squared over k squared. And that is a constant that, again, I want to talk more about, but it just is a constant that is the constant slope, the rise over the run of derivative versus derivative. That's the great news. Now, on the other hand, of course, each one of these pieces is an incredibly advanced, sophisticated piece of mathematics and science. Like anybody who can read this equation in this class, if you can even sort of see what it's saying at all, you've done a lot of good work already to this point, because it's obviously gibberish to the rest of the world, this equation. Like what it simplifies our life incredibly by making us know all these complicated pieces to put together along the way. Like you've got to get what it means to be a derivative and a second derivative and a partial derivative. But if you get all that, then this says put those complicated pieces together, and you'll see that a wave is this simple package. And this is what the part I want to say to get in your brains, like before we leave for the weekend. What it's saying is compare, and this is where I'll end, okay? Even if I can't analyze that constant today. Okay, well, wait. If you were trying to memorize equations or anything that important, certainly that I think you should just accidentally end up memorizing this or knowing this, but certainly in terms of any list of equations that you're running in your mind, to like this is certainly a big one. I'm going to try to quickly just compare in English to get you to understand it, and then leave, is like uh, this is like the more sophisticated version of Hooke's law. Like a wave pulse, it is made of harmonic oscillators, but it is more than a harmonic oscillator, right? A wave pulse is an oscillation of oscillators, really, right? Like a wave pulse is cosines happening in time and in space. So it's almost like the two-dimensional extrapolation of oscillation. In fact, it is. That's what I want to say right here. Like, look, if you go back to what we're trying to say about a mass on a spring, like a mass on a spring, there's some equilibrium position called y equals 0. There's some position, some place, some point, some zero-dimensional point called y equals 0 that the mass is trying to get back to. Like that's equal, and the mass is displaced from that place. It's far away from it. It's instead at some position called y or y naught or whatever. In other words, the mass is displaced along an axis away from it, along a one-dimensional region of space. It's displaced from its zero-dimensional home, right? Home is a point called equilibrium. The mass is away from that point. And what Hooke's law says is that the farther away the mass is, the greater a rate at which it will accelerate back to home. Like the rate at, if you pick a mass at any random point other than at the equilibrium position, the rate at which it will accelerate back to home base is directly proportional to how far away it is displaced from home base along a one-dimensional axis. Like that's what oscillation says. That's what Hooke's law says. The rate at which you accelerate back home is determined by how far away from home you are. Okay, that's what that says. Now let's look at the wave equation. On the left side is again acceleration. Acceleration, so let's pick some piece. We look at some piece in the wave pulse. It's accelerating at some rate along the y-axis back home, Now what is home? What's equilibrium in a wave pulse? I'm not asking you, I'm rhetorically asking, what is home base in a wave pulse? Well, home base is no longer a spot. It's no longer a position. It's not a point. Home base is the x-axis, is an orientation. In other words, equilibrium is when the whole string is flat, right? It doesn't matter where the string is, here or there or there. Equilibrium is the whole string being flat. That's what everything is vibrating back to. So equilibrium is now not a spot, it's a line. It's a one-dimensional orientation. That's what equilibrium is now in a wave pulse, is that one-dimensional x-axis. So if you're some point here, some random point that I'm this point, okay, you're want to get back home to that axis. You're going to accelerate back home to that axis just like a mass displaced from equilibrium would accelerate back to equilibrium, right? But here's the catch. If you're a little point in a wave pulse, like this point right here, the left side says, I'm going to tell you how fast you're accelerating back home, back along the y-axis to x-axis. The right side says, yes, that rate will be directly proportional. That rate at which you'll accelerate will be directly proportional to something. It will be directly proportional not to how far displaced you are from that point. No, like this is not y. This thing is a second derivative. It's second derivative of y with respect to x. In math, you whenever you're looking at graphs and stuff, you may remember when you're talking about first derivatives, you call them slopes, or first derivatives measure steepness, slope. The first derivative of a graph is how steep it is. The second derivative of a graph in a math class, if you're looking at like, and I actually am going to stop to ask everybody this, and I really will go after this, but I have to ask you, I can't tell you because I have to make sure. So I'm going to ask the question right now. This is definitely a 50 point or whatever, and you can all answer. It doesn't matter who answers it first, but I'll say the question. In math class, if you have like y equals f of x, if you have y is a function of x, like, and so it's math, so we're not worried about time or anything like that, but you have y equals f of x. In a math class, when you're thinking about what derivatives are, derivatives, first derivatives, slopes of tangent lines, they're supposed to measure steepness of the curve. But second derivatives measure something else in math class, like the second derivative of a y equals f of x graph. First derivative measures slope, how steep a graph is at a point. What does the second derivative measure in a math class? So I'll just say the question again, and I promise we will go like shortly after this question, or after you do something with this answer to the question, but I just want to make sure we're together because this is a lot of abstraction. In math class, when you have like y equals f of x, dy dx, you think of as slope. Like, for example, if the slope is 0, if the first derivative is 0, then you know the graph is neither going up nor going down at that point. It's like a maximum or a minimum. But yes. Wait. Yeah. Okay. Rate of change, yes. Oh, good. Sorry, I didn't even see in the chat. Rate of change, yes. But now what I'm saying is slightly more specific. All derivatives are rate. That's good. And thank you for participating. And that's 50 points, no matter what. All rates of change are, all derivatives are rates of change. But if you think of it on a graph, the first one specifically is like the slope of the graph. So like if it's 0, the graph has no slope, so it's not going up or down. So it's like a maximum point or minimum. But remember this, if the second derivative is 0, that means something else. It's like called an inflection point rather than a critical point or something like that. And if the first derivative measures steepness of the curve, the second derivative measures like steepness of steepness, or like, yes, rate of change, but then there's a word they use, and I have to get it from you guys. I can't tell you. You'll know it when you hear it. But in terms of the shape of the graph, like if first derivative measures like the steepness of the shape, the second derivative measures not just like whether it's angled up or down, but kind of more like how the whole shape is curving like a bowl or not. So like this whole business of whether the curve is very bowly or bowly up, or like a bowl up or a bowl down. You'll know it when you hear it. The second derivative in a math class measures, if the first derivative measures slope or steepness, the second derivative measures, what other hint can I give? Or maybe it's in the chat. No, like a point of inflection is in a graph is a point where the something is 0. If the graph is like looks like a bowl facing up versus if the graph looks like a bowl facing down versus if the graph is flat, we have a term for that. It's like something up or something down. Yes, it's exactly what I'm looking for. Sorry. Yes. And I'm not trying to put anybody on the spot. I just if I say like, I just have to absolutely make sure that it's connecting this. Yes. Concave is the word I'm looking for here. To everybody, this is not a quiz. Can anybody ever acknowledge, like now that you hear that, now that Durkel has said that, is that word, I'm not demanding that you can like do an exam on this word, but is that word familiar? Is it like somewhere in your memories? Fair enough. I'm not asking you to remember much about it yet. Okay. In fact, I'm not expecting you guys to remember any of this. That's actually why we're doing it. I don't actually think anybody gets any of this stuff from the first, but it's, that's fair. All right. In a very small, dark space. Look, I'm with you. And you got to understand it was like that for me too. I think most of you are actually better students than I honestly, and way smarter than I was or am in a lot of ways. You got to understand that. Like this stuff was fuzzy for me too for a long time. But it helps me if you even like know the word and kind of remember like when it came up, because what I'm trying to tell you now to appreciate more is that concavity is like the second level of slope. Slope is the rate of change of a graph. Slope of slope is concavity of the graph. Like if you think about like there's one level of like, is the graph even pointing up or not? And then there's another next level is like, is the graph, even if it's not pointing up, is it trending up? Like it's like acceleration, but in space. And so what I'm saying here, why I'm saying all this, and there's nothing to remember. What I'm saying is this: if you were I'm saying this, and I am looking at the time, and it's still, I mean, I know I'm sort of racing to really let you go early, but we're definitely not late or anything, but we still will go. What am I saying? Blah, blah, I'm losing my mind, which I never had. Oh, yes. See, where the math physics connection is, like where math and physics are the same, is we're all saying the same thing about derivatives and equations and functions and how they work. But math is saying this is how equations work. Like whatever, as long as you know what your dependent variables and your independent variables, here's how the relationship works. Physics is often saying now specifically we like to look at situations where time is the independent variable. And when we do that, then those derivatives on graphs, if time is this axis on a graph, then the slope of that graph means velocity in the like how fast something's moving through time and space. And the second derivative of that graph, the concavity of that graph, if what's here is time, if the independent variable is time, then the second derivative, the rate of change in time, is what physicists call acceleration and care about acceleration in space and time. But if your graph is just a y of x graph, and that's also valid, right? Like sometimes like we have the same shape here. What we're saying about waves is we're looking at a cosine graph, but for a wave, it's happening, that cosine, whether time is the independent variable or space. If space, when you're looking at space, in other words, when you've just taken a freeze frame of your movie, I mean, one frame of your movie, so you've held time still, and you're just looking at one chunk of a wave, right, going through the ocean or across your lab string, like what you see is that hump shape. That hump shape is y as a function of x. Well, at any given place on that shape, the first derivative is the slope of that shape. It's literally how steep, literally the string would be in space, right? Because that's how the string is shaped in space. And if you look at any second derivative, it's how concave the string is in space. Like there's no time at all if you're just looking at the x graph, right? So here's what I'm trying to say, and I really will. What I'm saying is the wave equation says that, or to go back, the wave equation, if we look at some spot, what the wave equation is saying is, here's how you know a wave is happening. Here's what a true wave pulse is it not just if you see a squiggle is not a wave. And not just if you see something going up and down in time, no, that's not a wave. But if you look at something that at any given moment, you look at it, you see a squiggle, and any place you look, you see something squiggling up and down. There's pretty good evidence that it's a wave pulse. And now what we're saying mathematically is it definitely is explicitly wave pulse if, and this is where we're going to end. I'm going to say this, I'm going to try to say this as clearly as I can, but it's a deep thing, I think. It really is a wave pulse. If you pick any point, like this thing that I keep making a huge white circle, you pick that random place in the whole system or on the whole surface of like ocean water, you pick that point. And you ask at what rate is that little point accelerating down the y-axis back to its home axis of x? At what rate is it accelerating down? The answer, according to the right side of this equation, the answer is, it's accelerating back home at a rate that's directly proportional to the concavity of the disturbance, the wave, at that point. In other words, the more concave that section of the wave is, in other words, the more stretched away the whole thing is from the x-axis, the more deformed, the more disturbed, the more contorted the more concave, the more non-horizontal the shape is at that point, the faster you will race home. In other words, it's exactly like Hooke's law. Hooke's law is the one-dimensional case. The farther away you are from home base, the faster you accelerate toward home base along a line. A wave is, the home base is now a whole line itself. Home base is not a base, it's an x-axis. And what it means to be home is for the string or whatever, the ocean surface, to be flat. The more bent we are from flat, the more concave we are, the more distorted we are at a certain place in time and space, like at any point, the faster that point will accelerate back to the home flatness. That's what the wave equation says, is that, and I'm saying the wave equation says, this, putting the cannoli down, the weapon down, and putting the pen down. I swear this is the last. And I might even not even check if it's clear or not. But this is the punchline I'm trying to say right now. Like, this is what the math, that equation is a huge equation. It is definitely, look, honestly, it's by far the most sophisticated equation that you've seen yet in physics or math, I think, or in any science. Like, it is an extremely, like, rich, powerful, rich with information, but highly sophisticated equation. It's called the wave equation. I've literally, I've taken over my life, I've probably taken 8 classes in physics, for various degrees, each of which was called waves. And it took me like at least 3 of those wave classes and all the math to even know what our subject material was, like what are waves in the first place. And I had one professor once who walked in on the first day and said, a lot of us do all this wave stuff and still have no idea what a wave is. I want to clarify that before we go any further with all the crazy math. And I was like, yes, good, please. What the heck is wave? And he said a wave is any solution to the wave equation, and then went on from there. And I like that's how that to him, that was satisfying. And I sort of see what he's saying now, and it is true. The wave equation, anything that fits the wave equation is a wave, and anything that is a wave fits the wave equation. And the wave equation says, in English, it says that acceleration back home is direct to the home axis, is directly proportional to distortion from that home axis. The more distorted the string is, the more distorted the medium is, the more distorted the water is, the more stretched a piece is, the faster it accelerates back to undistortion, to no concavity, to flatness. Acceleration is directly proportional to concavity, which you can think of as distortion. And here's the kicker: at every and any point in space and time, like everything I'm just saying, if you can picture it for one random point that you pick, like, oh yeah, okay, I guess the bigger the hump is, the faster this thing goes down. What I'm saying is, if something is a wave pulse, then what you just did in your mind must be true for every single point that you pick at every single point in time. For all of them, it's always true that the more bent the thing is right there, the faster they're accelerating back home. That is what wave motion is. That's where I want to stop. If you guys are vaguely okay with that for the moment, and I'll post a Google thing and we'll just keep going. But if that's okay, if I can get any okay or any thumbs up from anybody, we will end right there. Oh, now it's good. Oh, cool. Thank you, Ray. I almost just had a heart attack. Not really a heart. Okay. Let it sink in. And I'll put a video, blah, blah, but electron bless you all. True. And I mean that from the bottom of my cork.